if we kick off with Susanna Winkelbauer. She is a PhD student at the Department of Meteorology and Geophysics at the University of Vienna. And today, Susanna will be presenting on Arctic quality metrics based on oceanic transport for CMIP6. So please go ahead, Susanna.
Yes, thank you. Can you hear me well?
Yes.
Perfect. And can you see my screen now?
Yes.
Yes,
Great.
perfect. That's good.
Thank you.
Okay, just 1 second. Okay, yes. So thank you for having me. Yeah, I'm Susanna from the University of Vienna. I actually just finished my PhD 2 days ago and waiting on a postdoc position now. And today I'll
Sorry,
be talking...
Susanna, the view's just going into the presenter mode.
Okay, that's bad.
Before, when you first put it up, it was in the full screen.
Okay, give me a second. What about now?
Still in the presenter.
Okay, that's weird. And now?
That's it.
That's it. Okay,
great.
perfect.
Thank you.
Thanks. Okay, so yeah, I'll be talking about transports in the Arctic Ocean and how we intend to use them as quality metrics for CMIP6. Yeah, starting off, so oceanic transports, yeah, they play key roles in regulating the global climate and are important parts of the Earth's energy and water budgets. So the accurate monitoring of those transports is quite important, and we have multiple mooring lines in the oceans, which measure deep water velocities and other seastate variables. So for example, as seen here to the right, we have the Rapid Array and the oceanic array in the North Atlantic, with the intent to monitor the North Atlantic meridional overturning circulation, and also in the Arctic, and those black lines. So we have mooring lines in the main gateways in Fram Strait, the Barents Sea opening, and Davis Strait and Bering Strait. And what they have in common is that, of course, those are observations, they are limited, not only in space, but also in time. And therefore, it's quite important to compare them to transports from reanalysis and climate models.
Susanna, so sorry to interrupt.
Yes.
It's gone back into showing us the PowerPoint, so Eleanor's happy to share the slides.
Okay, yes, that's fine. That's fine with me. I think still one back. Yes, that's it. Yeah, so like I said, so our goal is to calculate transports for reanalysis and also climate models like CMIP6. Now, this isn't that easy, so we have some challenges due to the grids that are used by the ocean models. So for example, as seen to the right, this is a typical tripolar grid where instead of one North Pole, we have 2 North Poles over Eurasia and North America. And those curvatures which come with those grids, they pose some challenges concerning the grid orientations and the signs of the velocity components. So, for example, if we move towards the artificial poles now on those grids, we do not move towards the true north anymore. And next slide. Yes, perfect. So we can't just interpolate the data to regular grids, as we would get quite large interpolation errors, as seen here to the right. So here we see volume transports for the rapid section in the North Atlantic, calculated for one model on the model's native grids in black and red, and with prior interpolation to a regular grid in blue and orange. So we see we get those big errors. So we can't do that. We have to calculate them on the native grids. And as we have many models in CMIP6 with various grid types, this can be quite time consuming if we want to look at larger ensembles. And therefore, I'm going to the next slide, please. We created StraightFlux. This is a Python package. You can download it via PyP. And those are now new tools to calculate precise oceanic transports of volume, heat, salinity, and ice. We've tested them for various CMIP6 models. I think we've tried it for around 40 models and various reanalysis, and are quite happy with the results. Yeah, next, yes, thank you. So just shortly, some technicalities. So straight flux works using two different methods. The first one is the more commonly used one, the so-called zigzag method, where if we have a strait, in this case it would be Fremd Strait, the red line in the middle between Greenland and Svalbard. And if you want to know the transports through this strait, we try to follow the modeling grids as closely as possible along the cell faces. So this would be now the blue polyline. And we integrate the transports along this line to get the net transports through the strait. And then we have a second method, which is seen at the bottom. It works a bit differently. So for every grid cell surrounding the strait, we actually project the U and V components, so the velocity components in the ocean in the direction of the strait, so onto those yellow lines to get the transports that flow normally through the strait. And then in the end, so if we go to the next slide, please. Thank you. We can create those nice cross sections as seen here in the middle. So where we can assess the currents flowing in and out via those sections. So here in the middle, for example, we see the Barents Sea opening, so a section between Svalbard and Scandinavia, where a lot of heat is transported northward into the Arctic area. We can quite nicely see those inflowing branches in the southeastern part of the Barents Sea opening, where warmer waters from the North Atlantic move towards the Arctic. And to the left, we can see those net integrated transports for the historical period in black and two SSB scenarios in red and blue. So we can see those clear trends in heat transports in the Barents Sea. And now using the sections, we can assess and try to find where those trends are coming from. So if you go to the next slide, there hasn't changed a lot in the cross sections, especially in the currents one. But the temperatures, they get a lot higher. So we can say that those increases are mainly caused by temperature increases in the oceans. Yeah, next slide, please. So we've already tested those methods for various straits in the oceans, like I said, using reanalysis, but also climate models. And most recently, we've assessed the energy and water bodies in the Arctic with a lot of discussion on those transports. So if you're interested, feel free to check out this paper, Winkelbauer et al. 2024. And if we move to the next slide, here we can see heat transports for the Arctic. We see the seasonal cycles. So those are net integrated over all 4 Arctic straits. So it's really the net energy that flows into the Arctic in the ocean. For different CMIP6 models, all of the colorful lines. For reanalysis, the black line, and also for derived directly from mooring observations, the black dashed dotted line. So we can see we have really huge uncertainties and intermodal spreads for the climate models. And most models, they tend to actually underestimate the net heat that is being transported into the Arctic. So we see that most models lie below the reanalysis and observational estimate. Especially at the bottom, we have like a handful of models here, mostly in pink and light blue. They simulate really unrealistically low transports, which are caused, if we move to the next slide, mainly by heat inflows through the Barents Sea opening. So here now we have scatter diagrams between heat transports in the Barents Sea and volume transports to the left, and heat transports and temperatures to the right. All of the colorful dots are the different CMIP6 models. They are long-term averages. So we see we have very high correlation, both with volume transports and temperatures. So those heat transport biases are actually a result of biases in both those components. And looking at the temperature profile to the right, so here in black, it's maybe a bit hard to see, but here we have the reanalysis. So we see that the Barents Sea is quite shallow, but actually in all water layers, we see that the models tend to underestimate the temperatures in the Barents Sea. And if we now move on, those biases in the heat transports, they are actually also seen in other components in the Arctic system, like sea ice or the ocean warming rate. For example, here to the left, we see a scatter diagram between ocean heat transports in the Barents Sea with sea ice extent in the Barents Sea. And we see that models with lower heat transports, they actually simulate quite high sea ice extents. And this now in general leaves us two possibilities. So either higher heat transports lead to more sea ice melt and lesser sea ice areas, or the other way around. If we have more sea ice, this slows down the currents, cools the ocean, and leads to less or to smaller heat transports. Nevertheless, we see that those models with those really high biases, they also show biases in the sea ice extents. And next slide, please. Yes, so here we have the same, but with the ocean warming rate. So the change of energy that is contained in the whole Arctic Ocean. Again, we see quite high correlations. So we see that models with lower heat transports, they actually also simulate a lower or slower warming of the Arctic Ocean. And moving on, please. Yes. So now the next idea was to use those transports and their effect on those other components to actually use them to constrain models and to lessen uncertainties in model projections. So we really have quite large uncertainties in various projections of ocean and sea ice variables. Like, for example, here to the right, we can see the September Arctic sea ice area, historical and projected. We see quite high uncertainties for all model scenarios and also for the historical period. And the next slide, please. Okay, sorry, I inserted actually another slide. So those uncertainties, they can be caused, first of all, by uncertainties in the technical pathways that we will be taking and the emissions that we will be creating. But those uncertainties are covered by the, for example, the SSP scenarios in CMIP6. Then, of course, we have uncertainties due to natural variabilities, which come from the kind of chaotic state of the system. And the third one are model uncertainties, which arise due to our, as we do not fully comprehend the physics behind those changes and can't model them perfectly well. And this is where we want to start and try to lessen those projected uncertainties. And for this, there are many different possible ways. So there are constraining approaches. We can try to single out better performing models, or there are also different model weighting approaches. And quite a nice one is this one, which was first mentioned by Sanderson et al. And then further developed by Knutti et al. And Brunner et al., where actually models in the model ensemble are weighted dependent on the performance when compared to their two historical observations, and dependent on their independence of one another. So in general, models won't be performing equally well when compared to observations, and models tend to use similar or even the same modeling components in some parts. So this may skew results also towards a certain family of models. And now, while Knutti et al., so we can use various diagnostics to get those models, and while Knutti et al. Used sea ice itself to weight sea ice, we want to do something a bit different and try to do this with our heat transports. So next slide, please. And next slide. Yeah, so we see very high correlations between sea ice extents and the heat transports, and therefore we can move on to the next slide. Yeah, we want to use them in this weighting approach to try and lessen those uncertainties of the sea ice projections. Now, if we move on, and you can move on one slide further, this will be easier. Yes, perfect. Thank you. So here we see now sea ice extents for the SSP 585 scenario and the historical period. And in black, we see the ensemble mean for the unweighted ensemble. In blue, we see observations. So we see that actually in the historical period, the unweighted ensemble mean is a little bit lower than the observations. And then in red, we see the multi-model mean using our weighting approach with the ocean heat transports as diagnostics. We see that in the historical period, the multimodal mean actually moves towards the observations, so that's good. And we see an earlier ice-free Arctic. We see that the spread in the first year of an ice-free Arctic is significantly reduced. And we see that it agrees really well with earlier studies. So this light blue line would be the same weighting approach, but using other diagnostics, the same as Knutti et al. So if we move to the next slide, yeah, we see that for this diagnostics, for the sea ice variable, it works really well, independent of which diagnostic we use. So if we use heat transports, we get similar results as if we use sea ice extents. And now the next step would be to try the same approach when looking at other variables, like, for example, sea surface temperatures and ocean heat contents, and also try it with a larger ensemble with more models. So right now we have only looked at 30 models. And yeah, so this is still work in progress, but yeah, moving on. So the key points, so we now have those straight flux tools, which allow us for pretty easy and fast calculations of transports for various models. And with those, we can, first of all, analyze mean states, variability, seasonal cycles, whatever we want, of the transports, and also looking at cross sections, the vertical structures and flow patterns through cross sections. And now in this, what we are working on right now is that we are trying to lessen those uncertainties using heat transports to constrain the models in this weighting approach that I talked about. Yeah, so that's all from my side. I'm happy to answer any questions. I think I saw something in the chat. So,
Yes, so
yeah.
Christian, you've got a question?
Yes, thanks a lot, Susanna, for your talk. My question was, so I understand that your tool can use any kind of regular grid, but my question would be, can it also work with unstructured meshes, like specific models like FESOM would come with?
So that's actually what we are also working on right now. So it works on all different curvilinear and regular grids, but on unstructured grids, we are still having some troubles. So we tested it on FESOM 2, I think, and it worked, but we are still trying to implement all of the other unstructured possibilities. In the end, the goal is that it should also work on those grids, but it's not there yet. So it's still, yeah, a bit in the making.
Thank you very much.
Welcome.
And I think that's maybe answered Wilbert's question in the chat.
Yes,
as well.
I think so.
Has anyone else got any questions? Feel free to put your hand up. Louise?
Yeah, that was a really nice talk. This is possibly a relatively general question, but in terms of the heat coming into the Arctic, can you say something about how much of that is driven from the North Atlantic overturning circulation variations? Like how much of it is on that scale from the further south in the North Atlantic, and how much is specifically regional, the sort of variations in time and between the models that you're looking at?
Mm-hmm. So good question, but actually it's I think that it's really mainly driven by those waters coming from the Atlantic meridional overturning circulation, moving northwards next to Scandinavia and then entering mainly via the Barents Sea opening. So really this is the main import branch of those heat entering the Arctic in the ocean.